Hello, welcome back to Statistical Mechanics. I think it would be worthwhile to begin our course on statistical physics by remembering the contributions by Ludwig Boltzmann. We do this one as a tribute to the great physicist. And as we mentioned, the world has been so cruel to Boltzmann that he had to end his life. Ludwig Boltzmann, 1844 to 1906, was an Austrian physicist and philosopher, and he earned his PhD in physics at a young age of 22, 1866, in the year 1866, just 22 years, and his mathematical intelligence has been reflected in many of his path-breaking contributions in a variety of fields. And his philosophical ideas were such that it was questioned by many of the contemporary physicists, and one major idea of dispute was about the existence of atoms. It was well before the establishment of many of the theories on atoms, like the Bohr model or Rutherford model. We can see Boltzmann lived only up to 1906. And I think it's worthwhile to mention that Boltzmann died on September 5th on 1906. September 5th, of course, it's remember in India at least as Teachers' Day. So that is a point I think it's very easy to remember. Yeah. Anyway, we'll see that there are a lot of criticism that was invited by Boltzmann because of his belief in the existence of atoms, and much of his statistical mechanics contributions were based on his strong belief that all matter is made up of tiny particles like atoms. And he has made a lot of contributions to physics. The main contributions include kinetic theory, interpretations in kinetic theory, even though the kinetic theory distributions, most of the distributions were explained by Maxwell himself. The better explanations were given by Ludwig Boltzmann. Similarly, the second law of thermodynamics, which is regarded as one of the most fundamental laws of nature, which defines entropy in one way. The statistical interpretation was given by Boltzmann through his famous equation, as we have seen many a times. I'm repeating that equation because that equation is so historical, so relevant in the entire history of science. S equal to K log W or omega, and this W, I told you this is known as thermodynamic probability. This W actually, when I searched about why this W, I found that this W stands for a German word. And I'm not dare enough to pronounce that word. You try yourself. It's a German word which I will try to write it here. Even writing that, its spelling itself is challenging. Okay, you can just check it. That's better always. So it's a very long word. I don't know how to actually pronounce this particular word. We'll have to see the help of Tarurji or somebody at least. Or on Nigel sir, who is familiar with these words and all. Right. Okay, so this is W, and this German word means the probability of occurrence of a microstate. Okay, probability of occurrence of a microstate, and that's a German word. Okay, so that is why this particular W, okay, W is taken here in this equation. And also the probabilistic interpretation of entropy, Maxwell-Boltzmann distribution. Okay, you can see Maxwell's concepts and Boltzmann's idea, it were put together to understand the behavior of classical particles like atoms and molecules in a gas. So it gives Maxwell-Boltzmann distribution, and of course he is regarded as I told you, one of the forerunner in the development of quantum mechanics, because he at a very early stage he suggested that the energy levels of systems can be discrete. Discreteness about the energy level of system was explained, or it was coined by Boltzmann himself, and which was later established, and we have a number of proof for that as the basic building block or basic assumptions in quantum mechanics. And when we say about Boltzmann, we cannot forget some of his students who are very familiar to us. One is Ernst himself. We have discussed about Ernst, his contribution in the classification of the phase transitions into two categories: the first order phase transition and second order phase transition. That was a classification that was brought out by Ernst. And Ernst actually was the doctoral student under Boltzmann. Boltzmann was the PhD guide of Ernst, and as I mentioned in the previous video, like Boltzmann himself, Ernst also had a very sad ending to his life. Forget about it. Other students include Arrhenius. You have learned about Arrhenius equation when you studied about, I think, electrochemistry or something like. Nernst, whenever you studied about the Nernst equation in redox chemistry, right, the redox equation. So Nernst equation. So all these people were students to this great mind. So you can see when you learn about his history and all, he actually spent a great deal of his final years of his life defending his own theories, because he invited criticism from many of his contemporary scientists, and it's understood that he suffered from bipolar disorder, a mood disorder, because of all this criticism, and finally he, as we know, that he ended his life during a vacation by hanging himself. But you know that the contributions of Boltzmann is remembered by any student of science, basically, whether it is physics or chemistry, because we'll be using the Boltzmann constant throughout Kb. And the values of Kb and Avogadro number were confirmed theoretically, even though such a idea was proposed by Boltzmann years before establishment of the theories of atoms. The values were experimentally confirmed actually a couple of years after Boltzmann's death, and it was actually Boltzmann didn't name the constant K as Boltzmann constant. It was Max Planck who, understanding the relevance of the contribution by Boltzmann, who named K as Boltzmann's constant later. And so that's actually a very brief introduction to Boltzmann and his greatest contributions to the development of statistical mechanics or physics in general. Now we will see what actually statistical mechanics is dealing with in the next slide. So as I mentioned already, that statistical mechanics is regarded as one of the pillars of modern physics, because without the help of statistical methods or statistical mechanics principles, it's actually quite difficult to understand or to comprehend many of the theories, many of the phenomena that we explain in modern physics. Like see, in particle physics, you study about the behavior of photons, you study about the behavior of electrons, protons, all these things we need. Why do they behave differently? All these things have been explained by the ideas of statistical mechanics. Basically, you can see the branch has derived its name from two words. One is statistics and the other is mechanics. So basically, you can understand what actually is statistical mechanics. It's bridging the mechanics and thermodynamics, actually. Bridging mechanics with the thermodynamics. You know, thermodynamics is basically an empirical subject where we make a number of assumptions or laws, empirical laws, which we call as the laws of thermodynamics, based on observations. And there are not many questions that can be answered. Okay, always questions are limited. Questions end finally in these laws, right? But what this statistical mechanics does is it's trying to explain the observations of thermodynamics. It's trying to explain from very first principles the observations made by thermodynamics, starting from the concept of atoms. So the basic aim at studying is at studying the macroscopic properties of the system in terms of their microscopic properties. Statistical mechanics aims at studying the macroscopic properties of the system. What are the macroscopic properties of the system? Like the pressure, the volume, the temperature, the entropy, the internal energy, Helmholtz free energy. All these things are macroscopic properties of the system, right? And statistical mechanics is trying to connect these macroscopic properties, the origin of these macroscopic properties, in terms of microscopic fundamental properties, like position of particles, momentum of particles, how it is related. And you know that one kind of the first attempt to do such a microscopic description of macroscopic properties was actually kinetic theory of gases, where we have derived by using lengthy expressions and long steps, we could establish the pressure exerted by an ideal gas by using kinetic theory of gases. We are done in maybe our second module or so. Okay, so that was the first step. So kinetic theory of gases can be considered as the first attempt to give a microscopic description to the macroscopically observed properties of systems. And its advancement is what is known as statistical mechanics. Okay, so now let's see why this statistical mechanics is needed. Because you can see that statistical mechanics basically deals with the systems having large number of particles. And that is the thing to be understood. Systems having large number of particles. When I say large number of particles, there is some sort of the lack of clarity there. When it's a large, how large it is? Do I mean 100 or 1000 or say million or billion? All these are large, right? Okay, but remember, as you know, statistics, the branch of statistics basically deals with the idea of probability. Basically, statistics deals with the idea of probability theories. You have learned basic courses in statistics in your mathematics classes. Probability or averaging, right? Averaging, standard deviation, all those things. Okay, and you know that the concepts of probability or averaging will be meaningful when we have large number of data regarding anything. And for small number of data, the accuracy of the predictions made by statistics will be lesser and lesser, right? For example, if how confidently are we able to predict will there be rain tomorrow? How confidently our meteorological department is able to predict will there be rain tomorrow, and what will be the accuracy of that prediction? Maybe we make fun of them that okay, is not there was a prediction so that it won't rain tomorrow, right? All these things, once you understand what actually they are doing, they are actually applying the laws of statistics and why things are going beyond their expectation, because they are getting very less number of data points, because we are not having many number of weather stations. We have very limited number of weather stations which is able to collect limited amount of data. So automatically, when the data is not sufficient, when the pool of data is not sufficient, what will happen, the accuracy of the predictions made by statistics may fail, and that is actually a property of statistics. So when do you get accurate results, accurate predictions using statistics? Remember, whenever you have large data points. Okay, right? I can make it clear more. The idea of probability, once you understand it clearly, you will see that, suppose that you have an unbiased coin. Okay, you have an unbiased coin, a coin having head and tail, right? And we believe that the probability of getting a head on tossing an unbiased coin is how much? Half, is it not? And the probability of getting a tail is also half, and that is the belief on which right now we use tossing the coin, right? What do you mean by probability of getting a head and a tail is half, or they are equal? What does it mean? Does it mean that I'm tossing an unbiased coin twice and I will be getting 1 times head and 1 time tail? Does it mean so? It's no. You may get, in both the toss, you may get head, you may get tail, you may get 1 head and a tail. All these possibilities are there, but still we say that the probability of tossing a coin, getting head or tail are equal. In what way? You'll see that this probability becomes equal to half, or say 0.5, is it not? Because the total probability in this case should be equal to 1, right? 0.5 each, only when the number of tosses are large, means the number of occurrence of the event. That's the language that we are using in statistics. The number of occurrence of the event. What is the event in this example? The event here is tossing the coin. When you toss an unbiased coin very large number of times, then you will see that the probability of head and probability of tail will be approaching 0.5. That's the meaning. For example, if you toss maybe 10 times, you toss, the output need not be 5 head and 5 tail. It can be say 6 head and 4 tail. So what is the probability? We can see, okay, so it is say that it's 0.6, is it not? 0.6. Take that of head. Now you may feel that, okay, if you toss the coin for 100 times, so what you may get, you may sometimes get it something like 55 head and 45 tails, right? So you'll see that the probability of getting the head has improved further to 0.55, right? If you toss it 1,000 times, maybe you will get a bit more closer. Maybe you will get it, something like some 520 times head and 480 times tail. Can you see that? Both this number and this number, it's 0.52 if you take it as the fraction, and this is 0.48. Can you see that both of these number are approaching the in principle probability of 0.5 from both the sides, right? So when the number of tossing is 1000, it has approached this much, and if it is say 10,000, if it is million, if it is billion, you will see that the probability would have become 0.5, right? That's the meaning of probability. And you may be you might have heard of You might have heard of, okay, or you have seen, okay, casinos, right? Casinos, at least in films, which is very common in, okay, the European countries, right? So the very basic principle of, okay, behind casinos is also probability. See, you may be winning once or twice, but if you repeatedly play and play and play, the biasing of the casino table will be in such a way that there will be more priority for losing. The table will be made in such a way that, so the chance of winning once or twice is more. You may get interested, you will invest more and more, and what will happen? You are playing more and more times, so the number of events of playing increases. And since the table is not a biased one, there is always some favor for the house, for the organizers of the casino. The chance is that you will but finally, the more the number of players, the more the number of trials, the casino will be always having a lot of gains, right? And that is the basic idea of probability. And when we come to our thermodynamic systems, we are blessed to have large number of particles. How large? As large as 10 to the power of 23. The fancy number, Avogadro number. Even 1 mole of any substance contains this many number of particles. Okay? So we are predicting the behavior of very large number of particles of the order of 10 to the power 23. So we have got 10 to the power 23 data points. That's the meaning, and that's a blessing. And that's why when you do averaging of the behavior of this many number of particles, you will be getting some measure for the internal energy of the system, some measure for the entropy of the system, and all other measurable properties of the system taken from the average behavior of 10 to the power 23 particles, of the order of 10 to the power 23 particles. So as I told you, when the number of data points is large, the statistics will be a more reliable tool. And hence we can say that in order to analyze physical systems having large number of particles, statistical principles are one of the reliable tools. And that's why statistical mechanics always gives you very good results. Hope you understood the basic principle. There the probabilities will approach reality because of the larger number of particles involved. And you think in the other way. See, what is the basic method of mechanics? Basically mechanics, the Newtonian equations are used to explain the motion of macroscopic particles, say a cricket ball, right? How do we do that? We will be able to get the complete information of a physical system by constructing and solving n equations of motion. What is n? N is the degree of freedom. If you have a particle moving along x-axis, you have got one equation of motion for that particle. If it moves along y direction or in a plane, there will be two equations of motion, one in x and other in y. And if the particle is moving in space, there will be three equations of motion, one in terms of x, in terms of y, and in terms of z. And if you know the initial conditions, like initial velocity, you will be able to make a prediction regarding what will be the future of the system by solving these three equations of motion. So that is the basic method of mechanics. That's what you are doing in your mechanics. Just think of that. So if the particle number is very small, you can directly go for writing their corresponding equations of motion and solving it in terms of the initial boundary problem or boundary conditions. You will be able to make exact prediction like what will be the momentum in the next instant, what will be the velocity in the next instant, what will be the energy in the next instant. All these things can be understood by the basic laws of mechanics. But remember, it's possible only if the number of particles is limited. Say, if you have to analyze Avogadro number of particles in a gaseous system, what do you have to do? It's something hectic. Why? Because there are 10 to the power 23 number of particles. I don't know whether you are able to imagine what, okay, how big is this number? 10 to the power 23. 1 followed by 23 zeros. It's a number that we can't imagine. Okay. So if you have got this many number of particles, and if you have to study the mechanics of this many number of particles by the ordinary laws, then you will have to write down 10 to the power 23 minimum. Okay, in one dimension I am telling. Minimum 10 to the power 23 equations of motions and solve them by the knowledge of their initial conditions. And it's okay, you can see that even the modern supercomputer will not be able to process this many data for a very simple system within a given time frame. So it's very complicated. So the only thing that we can do to explain the behavior or to predict the behavior of such systems having very large number of particles is to depend upon the theory of probability, which is a statistical tool. That's why we say that statistical mechanics is used to study systems having large number of particles, and that is only possibility if you have to explain something. So it's a theoretical tool to study many particle systems. Always remember, we don't use statistical mechanics to study the motion of Earth around the sun or the motion of a cricket ball. No, we won't use. It's not the arena. You'll be using statistical mechanics only when the particle number or the number of particles in the system is pretty large, so that the probability idea will be giving you values which is very close to reality. That's one thing. That's why statistical mechanics triumphs with the help of probability theory. Right? Now, same thing only. Thermodynamical observations are explained on the basis of atomistic motions using statistical tools. Okay. I told you that at the time of Boltzmann, who developed many of the protocols for statistical mechanics, the existence of atoms was not well established. The atomic theories were yet to develop. You know. Okay, it was in 1913 or so that the Bohr model, okay, all those models are coming up. Until then, the very existence of atoms or the idea that systems are made up of tiny particles called atoms was not established. And that's where Boltzmann's philosophical intellect or Boltzmann's intellectual capacities are adorable. He believed in the very existence of such particles even before those theories were established, and believing in that theory, he spent most of the part of his life in developing an explanation for thermodynamics, which was developed over centuries of effort. All those laws of thermodynamics, including the challenging concept of entropy, was explained by Boltzmann. You have to think of how great that attempt was. Okay, there is no doubt. Okay, why a man will not commit suicide. Right. So, always remember the macroscopic properties such as pressure, temperature, volume, okay, which are nothing but bulk properties. When we say macroscopic, you just mean bulk properties. Properties of the bulk, not of the individual particles, are related to, or they can be related to, the average behavior of a large number of particles. And averaging, as I told you, is what is done by using statistics. Right? So that's why we are learning statistical mechanics, and that was my aim to tell you, because this module has been included in the syllabus just to give you an overview why this particular branch of physics assumes relevance, and how it is helping us to understand large particle systems better. Okay, so we'll discuss the other relevant concepts, including the Boltzmann's equation and what's its meaning, the distribution, all those things in the coming videos. Okay, see, I have already uploaded one quick reference note in your Google Classroom. You may refer to that notes, and that's just a summary of all those topics, and you can just use it. And at the same time, I urge you to minimum you go through the textbook book for study. Otherwise, it's quite a nicely written book, so you can just read that book or any other material that is available. There are a large number of videos available in YouTube, which will be quite interesting. I just was trying to stick on to what I wanted to tell you. So you can always refer to that. Those who are interested more, certainly to take up the course to a higher level, you can always read depending on the time available. So thank you. We'll just see in the next sessions.